Listen up. You will notice that there are model kits in front of you. Don't start playing with them yet. We will get to them, I promise. Okay, we are finishing the chapter today. All right. Our big focus today is going to be on predicting shapes of our molecules. But we do need to start off with a very quick, brief little topic, and then we will move into talking about shapes. So, this last little mini topic that we need to cover is very quick, and it's on a topic called formal charge. And let me tell you what a formal charge question will look like. Okay? They're usually in free response, sometimes multiple choice, but usually free response. And it would have two Lewis structures already drawn out for you for the same molecule. Like two different structures for the same molecule. And the question would say, which structure is the more appropriate structure? Prove your answer using the concept of formal charge. Okay? Well, I'm going to show you how to do that. So we're looking at two different structures for the same molecule, and this usually is for molecules that have a central atom that is exceeding the octahedral. So let's just review that for a second from last class. Can any nonmetal exceed the octahedral? How do you know which elements can have 5 pairs, 6 pairs, 7 pairs, 8 pairs? Third period and under. So we're talking about elements like phosphorus, sulfur, chlorine, selenium, bromine, etc. Okay? Now, the example I'm going to give you, that we're going to look at, is the sulfate ion. And as I said, a formal charge question is usually going to have the structures already drawn out for you. So, if you used the step-by-step process that we talked about last class and how to draw a Lewis structure, this is what sulfate would look like. I'm going to draw a second possible structure, and it's going to look a little bizarre. I would not expect you to be able to come up with this drawing. That's why these things are usually drawn for you already. But here is another possible way to draw sulfate. Strange as that looks. This is not something I would expect you to do. I would never want to see you drawing something like this, because just... Is that just a special exception? Let me finish talking about it. This will make a little bit more sense after I get through. Okay, two structures. The question says, which one is the more appropriate? And prove your answer with formal charge. Okay, well, what that means is we are going to calculate a formal charge for every atom in these drawings. Now that sounds like something that would take a long time, but actually it doesn't. Because, for example, if you look at this oxygen, do you agree that it has one shared pair and 3 lone pairs around it? Yes? Okay. Doesn't this oxygen have the same situation? And this one? And this one? Okay? So when we calculate a formal charge for this oxygen, all of the other ones are going to have the same formal charge as well. So let's do that. We'll start with this oxygen at the top. Based upon where oxygen is located on the periodic table, how many valence electrons does oxygen have? 6. minus, now be careful with this, how many lone electrons, not lone pairs, lone electrons, dots, 6, plus how many bonded pairs? 1. Just one bonded pair next to it. So 6 minus 7 is -1. This oxygen has a formal charge of -1. So does this oxygen. So does this one. So does this one. Okay? Now, sulfur is going to be a little bit different, so let's calculate that one. Sulfur has how many valence electrons? 6 minus how many lone electrons are around sulfur? 0. How many bonded pairs? 4. 6 minus 4 is +2. Let's write it in. Okay? Let's do the same thing for this guy. Leave that 6 where it is. The other numbers are going to change though. For this oxygen, what's it going to be? 6 minus what? 4 plus 2. So that's a 0. Is this oxygen the same as that other one? Yep. 0. How about this one? Yep. And this one. Okay. What about that sulfur in the middle? 6 minus 0 plus 8. Okay, -2. All right. First things first. Within this set of brackets right here, please, if you would, add up all the green numbers together and tell me what you get.
-2.
Okay? Add these green numbers up. What do you get? You should get -2 for both of them. You should always get the overall charge, if there is one, when you sum all of the formal charges. So adding them all together is not how we're going to make this decision. Here's how we're going to make it. The more appropriate structure is the one that has more formal charges equal to 0. So the second one. Okay? And guess what? As weird as this looks, this is how the sulfate ion looks in nature. It doesn't look like this. It looks like this. Okay? This is the more appropriate structure. Okay? Molecules will take the structure, take the shape, or no, not shape's not the right word. They will take the structure that gives the most formal charges of 0. This had none of the formal charges were 0. This one was. Okay? Now, let me be clear. I said this before, but I'm going to say it again. I would not expect you to come up with this structure. Okay? Because this does not follow our general rules on how to draw a Lewis structure. This is not something I would expect you to be able to create. It would already be drawn for you, and you'd have to say which one is more appropriate. If they're asking you a question about it, one of these structures is going to have some zeros in it. Okay? But, I mean, it could be that this one on the left has 2 formal charges of 0, and this one has 4 formal charges of 0. This one would be better. The more zeros, the better. Yes?
If you ever had that response,
Okay? You would say the structure on the right is more appropriate because it contains more formal charges equal to 0. That's it. Okay? You wouldn't even need to show this work right here. I would, however, write the numbers next to each element. All right. We are ready for the main event. Okay? Now, anytime you see this acronym, which we say VSEPR, I know if you're actually going with its pronunciation, it would be VSEPR, but we just don't say that. I don't know. Okay? Does anybody know what VSEPR, VSEPR stands for? Valence, shell, electron, pair, repulsion. Valence, shell, electron, pair, repulsion. Okay? But whenever you see that acronym, I want you to think shape. What shape? Anytime VSEPR is mentioned, they're asking you what is the shape, or what is the bond angle maybe, or what is the polarity maybe. Okay? But the point is, things take the shape they do, and it's really important today to get your mind out of 2 dimensions and into 3 dimensions. And I do realize for some of us that's easier said than done, okay? But the point is, things take the shape they do because electron pairs, bonded pairs, lone pairs, shared pairs, I don't care. Electron pairs do not like to be near each other. And why would that be? Why do they repel each other? Because they have the same charge. They're both negative. Okay? So pairs, electron pairs spread out, remember, in 3 dimensions as far apart as they can. Now, blah, 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 blah. Here we go. Here's what I'm going to do. Okay? We have, let's see, 10, 15 shapes to learn today. Okay? What I am going to do is give you an example. I'm going to write it up on the board. I'm going to ask you to draw the Lewis structure. We're going to look at how do we predict its shape, and then we're going to build it with the model kits. And I think you will find as we go through this, this is not only an exercise to help you, remember and learn new shapes, but it's also going to help you to get faster at drawing your Lewis structures. So here we go. Here is your first one that I want you to draw. Carbon dioxide.
See, what I did was I just started.
All right, your drawing should look like this, or something close to it anyway. Let me help you get your bearings on what these columns represent, okay? Electron pairs is somewhat confusing, okay? This is how the chart is labeled in your book, but electron pairs, first of all, anything in this column applies to the central atom only. And instead of thinking about how many pairs are around carbon, what I would rather you treat this column as how many sides of carbon have something on it. 2. Okay? The reason I'm saying 2 and not 4, on the previous slide, there is a statement that says multiple bonds count as one shared pair. Not in a Lewis structure, but when we're talking about shape, a multiple bond is treated like a single bond. So this column, what I'm really saying is how many sides of the central atom have something on it? 2. Of those 2 sides, how many have bonded or shared pairs on them? 2. Are there any lone pairs around the central atom? No. Ladies and gentlemen, that is linear, which looks like this. You must use the red piece for this one. If you want to build it, build it. Now, not only are we going to talk about shape, we're also going to talk about bond angles And if you look at this one, the bond angle between the terminal atoms, what is this bond angle? 180 degrees, okay? We're also, as we go through, going to talk about polarity. And the question you want to ask yourself is it symmetrical? Yes or no?
Yes.
This one is symmetrical, so what does that mean? Non-polar, okay? Linear structures, in general, are going to be non-polar. Do you remember the AP Chem lingo for how to say that? Close. Bonds. The linear shape cancels out the polarity of the bonds. That's how you get around saying that, okay? Now, just to be clear, what if I did this? What if I made this change? Okay, it's still linear, but because those terminal atoms are not the same element, and thus because they have different electronegativities, it would now be a polar molecule. So, guys, there are some shapes that I'm going to go through and say, you know, like linear is a non-polar shape. I'm assuming that the terminal atoms are the same element because they usually will be. If the terminal atoms are ever different, I don't care what the shape is, it's automatically polar, always. Here is your next one. Boron trifluoride. Draw it. Why is it okay that boron only has 3 pairs around it?
It's an exception to the octet rule.
It's an exception to the octet rule. Boron wants 3 pairs around it. Okay? Now, how many sides of boron, our central atom, have something on it? 3. Of those 3, how many have our shared pairs? All 3. No lone pairs. Okay? Ladies and gentlemen, this, you must use the purple piece for this one. It's called trigonal planar. Make yours look like mine. Okay, geometry superstars, what's the bond angle? 120. 360 divided by 3 is 120. Okay? What do you think? Polarity, yes, it is non-polar. Okay? And we will see this word again, planar. Planar means flat. It is a flat molecule. Okay? Non-polar, so this is again an example of the shape cancels out the polarity of the bonds. As long as what? Same terminal element. Okay? Let's continue on. Nitrite. The nitrite ion. Draw it. Your drawing should look something like this. Now, guys, this is an excellent example of where your two-dimensional drawing is not going to look like the three-dimensional shape. I don't care what shape your drawing takes. Some of you may have drawn this in like an L shape. Fine, I don't care. I drew mine straight, you don't have to. But be assured, it is definitely not a linear molecule. Okay, so here is the thought process. How many sides of nitrogen have something on it? 3. Of those 3, how many have shared pairs? 2. And there's one lone pair. Ladies and gentlemen, in your mind, 3 sides. 1, 2, 3. Pick it up. 3 sides occupied. 2 of those sides have shared pairs. 1 has a lone pair. Here's the thought process. In your mind, I want you to think, okay, this shape is starting out trigonal planar because it has 3 things on the sides. But one of those 3 sides is not a shared pair. It's a lone pair, so pull it off. That doesn't look linear to me, does it?
Bent.
That is bent. Okay? Now, I know to you and me, using these models, it looks like there is nothing in this third position, but there is. What is there? A pair of electrons, this lone pair, and it takes up space. It has volume. In fact, and this is something written on the previous slide, it has a greater volume. It takes up more space than a shared pair. So, what was the angle when this was still here? This was 120. It's not 120 anymore. This lone pair that's sitting up here takes up more space than the shared pair, so it pushes a little bit. Here's what you say for the bond angle. Slightly less than 120. You don't have to give a number, an exact number, you just say slightly less than 120. And if you are asked why, the AP Chem lingo is to say that the lone pair takes up more space than a shared pair. How about polarity? Polar. How do you say that how do you explain why this shape is polar? The bent shape does not cancel out the polarity of the bonds. Okay? By the way, bent, always polar. You can't say that on a test, but that's a true statement. Okay? Moving on. This is a quick one. CH4. Okay, your Lewis structure should look like this. 4 sides occupied. All 4 are shared pairs, 0 lone pairs. Ladies and gentlemen, to build this one, you must use the black piece as your central. This is tetrahedral. Tetrahedral, does anybody remember the bond angle? For those of you that learned it? 109.5. Write it down. 109.5. What do you think? Polar or non-polar? Non-polar. Here's our next one. Ammonia. Draw it. Okay, here's another example where my 2-dimensional drawing is not the way it looks in 3 dimensions. How many sides are occupied? 4. Of those 4, 3 are bonded, 1 is a lone pair. In your mind, you need to think, this is beginning or starting as a tetrahedral. But 1 of those 4 occupied sides is a lone pair, so pull it off. That is trigonal pyramidal. It's not flat. It's a short, squat little tripod. Yep. Trigonal pyramidal. What do you think about for the bond angle? Slightly less than 109.5. Polar or non-polar?
Polar.
Polar. Trigonal pyramidal is always polar. The shape does not cancel out the polarity of the bonds. That should be a quick one. H2O. This is probably the most commonly missed shape right here. Not necessarily for water, because I know a lot of you know the shape of water just because you know it. But when you have other elements and this is what you draw, I can't tell you how many people will say this is linear. It is not linear. It looks linear in 2 dimensions, but it is not. Okay? This is another example where something is starting off, since it has 4 occupied sides, starting off as a tetrahedral shape. This time I'm going to pull 2 of them off for those lone pairs. Definitely not linear. This is another bent. Okay? Bond angle?
Slightly less than the
It's still, you don't have to say like slightly less than, slightly less than. It's just slightly less than 109.5. You don't have to say it twice or anything. Okay? Okay.
You don't have to.
So, trigonal pyramidal was slightly less than 109. This is like even more slightly less than 109, but you don't have to say that. You just say still slightly less than 109. What do you think? Polar or non-polar?
Polar.
Polar. Bent is always polar. Now, besides the bond angle, what makes this bent different from the other bent?
There's 2 lone pairs of electrons.
This has 2 lone pairs of electrons, and this one only had 1. Okay? Now, believe it or not, that is the extent of the shapes that most of you learned in Chem 1. That's it.
Yep.
Some of you, if you took honors and not even all honors classes, some of you may have gone on to some of the extended shapes, but not many. All right? So we're going to get fancy now. PCl5, phosphorus pentachloride. Ladies and gentlemen, 5 sides occupied. Why is it okay that phosphorus is exceeding the octahedral? It has an available D sublevel. All 5 are bonded. 0 lone. You will need to use, the purple piece as your central atom and fill it up. It's called trigonal bipyramidal. I find it helpful to look at this shape. This analogy is going to come in handy later on. I find it helpful to look at this shape as like a person standing up, feet, head, their arms are out like this, and they have a tail. Okay? Tail. Feet, head, left arm, right arm, tail. Now, ladies and gentlemen, this shape, unlike any of our previous shapes, has more than 1 bond angle. Now, let me tell you something. When you get to shapes that have more than 1 bond angle, you're not going to be asked the bond angles of those shapes. But just for my purposes, what does this angle look like to you? 90. What about this one? 120. 90, 120. 2 different bond angles. Polar or non-polar? Non-polar, as long as
The same
same terminal
terminal.
elements. Okay? Moving on. Sulfur tetrafluoride. Now, I love this example for a very good reason. Some of you, particularly when you get to your test, which is I don't know when, are going to get a little lazy with this. And you're going to look at something like this and see a central atom and 4 things, and you're going to go, I bet that's tetrahedral. It's not. Don't get lazy. Always draw it out to make sure. Do you agree that this has 5 pairs around the central atom?
Yes.
4 out of the 5 are bonded. 1 is alone. Now guys, this is why this is an AP extended shape. It starts off trigonal bipyramidal. But I'm going to pull one of them off to represent that lone pair. Does it matter which one I pull off? Yes. You cannot pull off any one that you want. And that's why I use this analogy. Okay? Feet, head, left arm, right arm, and you have a tail. If somebody comes along and says, I'm going to chop something off, of those feet, arms, head, tail, which can you most afford to lose? Tail. Tail's going. Okay? The first lone pair aligns itself around that trigonal planar center. And I did not make this name up.
Seesaw.
It's called Seesaw for a reason. Not that I'm going to ask you, but what would you say for the angles?
90.
Slightly less than 90, slightly less than 120. But again, I'm not going to ask you those on a test. Polar or non-polar? Polar. Chlorine trifluoride. Draw it. Again, trigonal bipyramidal. What did we say was going to go first?
Tail.
Tail? I would go with an arm. Yeah. Okay? And ladies and gentlemen, that is called T-shaped. Yeah, really. Now, to be perfectly honest, it's not a perfect T, it's kind of a sad T. Because those lone pairs are pushing. So what would you say for this bond angle that you do need to know? Less than 90. Because it's sort of a sad T.
Polar.
Polar, yes. Polar.
Polar.
Draw that, please. This is the last one in this family. Trigonal bipyramidal. We lost a tail, an arm, and another arm. What is this? It's linear. It's linear. What's the angle?
180.
Exactly 180. These lone pairs are pushing equally up and down. So it balances out. It's 180. What do you think? Polar or non-polar? Non-polar.
Linear.
Because it's linear. Okay. Folks, at this point, I'm gonna start to speed up a little bit here because you're starting to get the point. Okay? I'm gonna have you draw one more out and then we're gonna pick up the pace here.
Octahedral.
Draw it. Sulfur hexafluoride. Ladies and gentlemen, this shape, octahedral, you need to use the silver or gray piece as your central and fill it up. I don't know if we've talked about this yet in this class or not, but if there are 6 bonds, yeah, that oct prefix, which means 8, where's that coming from? 8 faces. 8 planes, like that. Okay? What do you think for bond angle here? 90 all around. You need to know that one. What do you think? Polar or non-polar? Non-polar. Non-polar. So, at this point, people, I'm going to start speeding up. And honestly, because I'm running out of examples, okay? If you have this situation, 6 sides occupied, 5 of them are bonding, you've got 1 lone pair, does it matter which arm I pull off? No. That, ladies and gentlemen, is called square pyramidal. Okay? Square pyramidal. Bond angle? Slightly less than 90. Okay? And polar. It's definitely not symmetrical from all angles. If you go one more, think about it. Remember, the entire purpose of these shapes is that electrons want to be as far apart from each other as possible. What do you think the next one is that I'm going to pull off? The one on the top. That is square planar. Remember, planar means flat. It's a flat X, or T, however you want to look at it. Okay? What about the angle on this one? Exactly 90, yeah. Okay? Polar or non-polar? Okay, now, this brings up a point that I forgot to mention on the last slide. In your Chem 1 classes, some of you, maybe not all of you, but some of you, when we were discussing if a molecule is polar or not, you may have used a flow chart. Okay, I know my students did. And one of the questions in that flow chart says, are there lone pairs on the central atom? And if you said yes, that automatically meant it was polar. People, if you have that flow chart, throw it in the garbage. It doesn't work for these extended shapes. This has lone pairs, one on the top, one on the bottom. But this is a non-polar molecule. It worked in Chem 1 because you were using the simpler shapes. When you get to the more complicated ones, it doesn't work. And guys, I hate to tell you, there is no magic formula to figure out if something is polar or not. You have to be able to visualize it and ask yourself, is it symmetrical or not? Okay? If I need to pull one more off, does it matter which one? This looks familiar.
T-shaped.
T-shaped. And again, it's that sort of sad T. Okay? So, what's the angle?
Slightly less.
Slightly less than 90? Polar, non-polar? Polar. And to finish this up, where do you think we're going to end here? Linear. The circle of life, everybody.
Yay.
The end where we began.
With a line.
With a line.
All of these.
Non-polar, 180 degrees exactly. Now, I'm going to put something up here that's easier said than done. Do not memorize.
What?
She says that.
But I wrote it all down.
Good, I'm glad. Okay, now, here is the thought process. And again, this is easy for people who are visual spatial and very challenging for those who are not. I would really rather you not memorize this chart. What I would prefer is that you think, what is the starting shape? And then imagine yourself pulling pieces off to represent lone pairs. During the test, in years past, guys, I've seen some crazy people do things. Crazy people doing crazy things. Not crazy people. Okay? I don't know when we're taking this test, but in the past, I've seen people like seem to go into like a meditative state, like they're closing their eyes and imagining. I've seen people doing like, I've seen people doing that. I've seen people ask for paper so that they could build little paper models.
We have the kids.
You can't have the kits.
Why?
You can't. Okay? But I have seen people do things, whatever is going to get you through the day, fine. Except you can't use the kits.
Oh.
All right? Now,
Can we bring our own?
no. No, you may not. Now, I realize that some of you are absolutely incapable of visualizing these shapes, visualizing yourself pulling pieces off. If you are incapable of that, you may have to memorize them. And there's no way around that. Okay? Do what's going to work best for you. What I would advise you to do in the beginning is use this chart to help you. The more practice you do, I think you'll find that you're using it less and less and less. Okay? So, whoops. Wait for it, if you feel like you would like more practice, here it is. If you feel like you've got this, then don't do it. Guys, remember, I just want to refresh your memory. Listen, if carbon is in a compound, it has to be the central atom. Good. if you feel like, that wasn't that hard, great, good. Drawing them, not too bad. Shapes, maybe a little tricky at times. But I will tell you what is the trickiest part of this, is deciding whether the molecule is polar or non-polar. Now let me say something about the way you decided that question in Chem 1. I don't know if whatever teacher you had gave you this, but a lot of us at Oakton, we do this. There's a flow chart that helps you decide whether something is polar or non-polar. Throw it out. It doesn't work. It worked in Chem 1 because we were only using the really simple shapes. For example, part of the flowchart said something like, if the central atom has lone pairs on it, it's automatically polar. That doesn't work anymore. There is no flowchart, guys. There's no way to figure it out. You have to be able to visualize the shape and ask yourself, is it symmetrical in 3 dimensions or not? So, let me scroll back up and let's talk through some of these. Okay? Let's look at this first one. Don't just look at the Lewis structure. Guys, you've got to think about what the shape is as well. Tell me, polar or non-polar? It is polar. Okay, now let me say something. Shapes that are linear very often are non-polar. Okay? But why is this one polar? The central atom is joined to 2 different elements. Okay? So that one is polar. How about the next one? Polar or non-polar? Polar. Folks, if you go back to the beginning of this chapter, there are some shapes that no matter what the atoms are, will always be polar. And anytime you see the word pyramidal, trigonal pyramidal, square pyramidal, whatever, anything pyramidal, always polar, no matter what. How about the next one? It is polar. Bent, both bents. Bent is another shape, always polar. Do not look at this in 2 dimensions and say, yeah, that looks pretty symmetrical to me. Remember it in 3 dimensions. How about ammonium? Polar or non-polar? Okay, non-polar. Do you remember the AP Chem lingo to explain why it's non-polar? Thank you. The tetrahedral shape cancels out the polarity of the individual bonds. Perfect. Let's keep moving down. How about this guy, square planar? Polar or non-polar? Think about what it looks like in 3 dimensions. It is non-polar. That's why that lone pair rule, throw it out. It doesn't work anymore. How about this one? Polar or non-polar? It is polar. Okay? If you wanted to say it in AP Chem lingo, square pyramidal is a shape that does not cancel the polarity of the individual bonds. How about this guy? Polar. Although linear, the central atom is joined to 2 different elements. N3 minus, what do you think? Non-polar. And the last one. Trigonal planar is usually a shape that cancels the polarity, but carbon is joined to different elements. Okay? Ladies and gentlemen, that is the end of the chapter.